Okay, so for some reason I failed to record this part about CYK because it was in a different file. Whatever. Let me do it now because it's a really cool example of dynamic programming. So, what is the problem? I give you a context-free grammar, right? So we already know everything about regular languages. We know how to recognize words in the language and so on. But context-free grammars, the problem is harder. So I give you a context-free grammar, I give you a string, I would like to know if the string belongs to this grammar. Can the grammar derive the string? And the reason why we care about it is because most programming languages are context-free. So they specified using a context-free grammar, and the code to parse them in the compiler use automatic tools that generate the parse tree, and which is kind of the second step in compilation. Right? The first step is lexicographical analysis, and the second step is parsing, and later on comes all the other step of compiling a program. Okay, so context-free languages as such are very useful, right? Here's, for example, an example for the context-free grammar for the language C or some subset of it. There are some languages that are not context-free grammar. For example, C++, I think is the grammar is more complicated, and parsing C++ program is a real nightmare. Okay, anyway, so the official problem is the following. I give you a grammar specified with variables, terminals, rules, a collection of rules, and start symbols. And I give you a string over the alphabet T, right, this one. And I ask you, is the word in the language of G? And really what we want for compilation, we don't really care if the word is in the language. We care more about computing the parse tree itself, which would, follow immediately from our algorithm. Okay, so we are going to assume that the grammar is given to us in Chomsky normal form. Chomsky normal form is a very clean way of stating in grammar. Every grammar can be converted into Chomsky normal form, but it can result in a big blow up in the size. But from our point of view, it's not a problem. This is just to keep things simple. So production of all of the following rule. A variable can derive two other variables. Or alternatively, a variable can derive a single letter. Okay. And if epsilon is a language, then the start symbol can derive epsilon. But that's the only place in the grammar where epsilon appears. So the parse tree of Chomsky normal form grammar is very simple, which is why we want to use it for the dynamic programming. And CYK is after the three people that came up with it, Koke, Younger, and Kasami. I hope I didn't mispronounce their name. Now, what is the basic idea? The basic idea is that consider the string W and consider all substrings. For every substring, we would like to write down, we would like to figure out what variables can derive those substrings, right? Now, it's very easy to do for one letter, right? Every one letter, we can just look for all the rules of a variable derive a single character and just mark down the variables. So that's easy. And then we are going to start looking on longer and longer strings, right? We first handle the strings of length 1, then we'll handle the string of length 2, figure out what variable can derive what string of length 2 that are in the string. Then we'll figure out what variable can derive a substring of length 3 that belong to the string, and so on. We will do this climb up until finally in the top we will have, can the start symbol derive the whole language? And that would be it. So that's the basic idea. Now, of course, the critical thing is that our rules are of the form x derive yz, right? So if I have a string like that, this is some this is some substring of W, right? We are looking on a substring of W, and we have x derive yz. then we have to pick the parts, right, and say, okay, this whole string, or this whole substring can be derived by y if the left part can be derived by x, can be derived by y, right, and the right side can be derived by z, right? So the idea is that we have a string, it can be derived by x if there is a rule such that the x derive y z, such that y derive the left side and z derive the right side, right? So if we have this rule, then we know that x can derive the whole substring, right? So this is really a bottom-up algorithm where you start building on bigger and bigger strings to figure out which variable can derive them. And the important thing for us is because all the rules are a variable goes to two variables, we really need to just guess the breakpoint in the substring when checking if it appears or not. Okay, so that's the basic idea. Okay, so let's see an example of this idea in action, and then afterwards we will describe the algorithm. So here's this grammar. So this grammar, it's a very simple grammar, and it generates a language that you know very well, but it's hard to see it from this grammar. Okay, I would come back later and show you how to derive what grammar it generates, what the language of this directly. But for the time being, I want to decide whether those two strings are in the language. Okay, so we are going to just do it, right? So let's start with the first string, 000111. And initially we just start with the input string. Now what we do, we figure out for all substring of length 1 which variable can derive them. Well, the zeros can be derived by A, and the ones can be derived by B. Okay. The more interesting thing is the next level, right? Because, I jumped 2 levels. Okay, sorry. So Y, ignore this row for a second. Now let's look on substring of length 2, right? And it's easy to see that the only possible substring of length 2 that can be generated by variable is this string. It's 0, 1, because Y goes to AB. In fact, we should also say YS here, but it doesn't really matter. Y or S both generates AB, and as such, they can generate the string 0, 1. Right? So that's how we fill this entry here. We also have to write, as I said, S here in the Y, but let's ignore this issue for a second, but it wouldn't be relevant. Now we want to derive strings of length 3, right? That's the next iteration. And we look on the string that starts in this position, right? So this is the string 0, 0, 1, right? 0, 1, we already know that Y can derive it. And X has a rule that goes to, X has a rule that goes to AY, right? A is just a way to write 0, right? So this is going to be A and Y. Let me maybe clean it together, clean it up a bit. A and Y, they go to X, right? We are using here X go to AY, right? A, here we are the corresponding is, this is the A part, this is the Y part, right? So we get X, okay? And the next level, X corresponds now to the string 001, right? But we can now use the rule Y goes to XB, or S goes to XB, right? So in both part we get, this is the part that goes to X, and then we have this part that goes to B, right? So we can generate YB here, starting at this symbol, right? Generating the string 0011. Okay, so that's how we get YS here. And then the next level is X, right? Because X can go to AY, right? So we have this string of length 4, 0011 that we can generate and here we have a string A, so this is a y, right, deriving x. So we get that the string 0, 0, 3, 0, 2 1s can be derived by x, right? Okay, and finally we go to the length 6, and you observe that s can goes to xb, right, which is indeed the desired string, right? So s can derive the whole string, and as such, yes. The answer is yes. This is in the language. Okay, you can do the same thing with the other example, right? It's the same kind of logic, right? The only difference, this is string of length 5, and then when you go to the next level, you just realize that you cannot generate it. So this string is not in the language. And if you want to more details, you can go and look in the slides. Okay, let me before I finish up. Let's figure out what this grammar really is. Okay, because that would be, and in fact, you have to kind of do it in the right way. So A, B, we already said it's 0, 1, right? So this is really y going to 0, 1, okay? Or it's going to xb, right? xb, right? So, but x has only one rule that goes to ay. So this is really ayb, right? This is the equivalent way of writing it. But we already said this is equivalent, as we already said, to this is already equivalent to y going to 0, 1 or 0, y, right? 0, y, 1, right? So this clearly, the language of y is clearly 0 to the I, 1 to the I for I larger or equal than 1, right? Okay, so this is the grammar of y. Now let's go to the grammar of s. S can derive epsilon, so epsilon, right? Or AB just means 0, 1, right? Or it derives XB, right? But X only is, so XB to remind you is just AYB, right? So as such, this is just 0. Let me maybe write it more carefully. This is just 0, 0i, 1i, I larger or equal than 1, very important, 1, right? So we have epsilon, 0, 1, 0, this language, so this is of course just our old nemesis, 0 to the I, 1 to the I, for I larger or equal to 0, for I larger or equal to 0. So this is what this grammar is, right? So Chomsky normal form is might be convenient for algorithm, but it's not very fit for human consumption. Okay.